All right, welcome back to the drive-through, boys and girls. Hope everyone's having a great end of their first quarter. This is 11-4. It seems so harmless. Tangent vectors and normal vectors, you're like, oh, this is going to be no problem at all. And it's really very easy to understand, but you'll start to see that these are going to get kind of ugly. And then you're going to start getting confused about whether or not, like, for example, the principal unit normal vector, whether that stands for acceleration. So I feel you, so just stay with us. Okay, so look, as always, if we start with some position function, come on. Everybody okay with that? All right. So, a unit tangent vector. Well, first of all, we are going to refer that as capital bold T of T, okay? And that is equal to R prime of T over the magnitude of R prime of T. Okay? Now, this on the bottom, this denominator is going to get ugly because you're taking the square root. See this over here? I just gave you an example of why it's going to get ugly. You're taking the square root of the squares of three functions. So it's just not going to be a pretty result. Okay? Now, the principal unit normal vector, I will explain later what the heck this is. But we call that capital bold N of T. Okay? And to find that, you take the derivative of the of the unit tangent vector over the magnitude of the derivative of the unit tangent vector. Now, I know what you're thinking. Hold on, it was a unit tangent vector. So shouldn't the magnitude of the derivative be 1? No, because you're taking the derivative of it. Okay? Now, there's going to be a couple different places, or a couple different ways that we're going to find the components of acceleration. So I'm not going to list them all. I do, if you have your book open, I would like for you to turn to page 828. I'm going to give you that chart for your test. Okay? What you find on 828 will be provided for you on the test. It's a summary of all of these components of velocity, acceleration, and curvature. You don't know what curvature is yet, but you need to understand today's lesson to get it. Okay? So, we will just refer to as the tangential component as lowercase a sub t, and we will refer to the normal component as lowercase a sub n. So that's our first slide. Okay, so let's just do an example. Find a unit tangent vector of the curve given by this. Well, if you remember, if we let x equal t, then y equals x squared. Okay, and so this is a parabola. Okay, a normal parabola that has not been shifted or altered, and so the orientation is going to be left to right as t increases. Okay, so r prime of t is going to be 1, 2t. And the magnitude of r prime of t is going to be the square root of 1 plus 4t squared. So, t of t is simply 1 over radical 1 plus 4t squared, comma 2t over radical 1 plus 4t squared. Okay? So let's put in a value for t. Let's do capital T of 0. Let's do capital T of 1. That's going to be 1, comma 0. Let's use a different. So, a unit vector, well, notice that that's a unit vector, so that's kind of nice. And as our particle travels down this curve instantaneously at the origin, 0, 0, you can see that its direction is all, so hold on, not its direction, this is tangential. Its direction is all going horizontally at that point. If we look at what happens at 1, comma 1, what do we get for that? Or at t of 1, sorry, at t of 1. 1 over radical 5, and then, sorry, 2 over radical 5. Notice that that is a unit vector, and it looks like it's going to be going, if you will, twice as vertically as it is horizontally. Does that make sense? Okay? So that's pretty easy to understand what the unit tangent vector is showing us. It's when we get into the second one, the principal normal unit vector, where things are going to probably confuse you a little bit. Alright, we're back. Now we are asked to find the principal unit normal vector. Okay, let's review all these words. Principal, well, it's with an A, so it's your friend. Okay? Unit, it's one length long, 1 unit long. Normal, in this case, doesn't mean that it's a unit long. It means that it's orthogonal to the motion. Okay? There are infinitely many vectors orthogonal to the motion. The principal one is going to turn towards the concavity. That's why it's the one that we care about. Eventually, it's going to put our motion in a plane, and that'll help us out for a lot of reasons. So, understand that everything we're dealing with here is also going to work in 2 space. It's just harder for me to show you, in 3 space. So, to find n of t, how do we find it again? That's right. It's the derivative of t of t over the magnitude of the derivative of t of t. So, let's just find t prime of t, and to do that, it will help us to rewrite this as 1 plus 4t squared to the negative 1/2, comma, oh my gosh, chain rule, 2t times 1 plus 4t squared to the negative 1/2. And now you guys are starting to see why this is such an ugly chapter. So let's catch my mistakes. T prime of t is going to be, alright, the derivative of this thing is negative 1/2 times 1 plus 4t squared, right, to the negative 3/2 times 8t. We'll come back and clean that up later. Okay? The derivative of the j. So, it's first 2t times the derivative of the second. Well, luckily, I think the derivative of the second is this, isn't it? So I'll just recopy that exactly how it is. Negative 1/2 times 1 plus 4t squared to the negative 3/2 times 8t. Alright, first times the derivative of the second plus second, okay, that's a little easier, 1 plus 4t squared to the negative 1/2 times the derivative of the first times 2, and that's that. Hey, welcome back. Okay, so this is all we've done is cleaned it up. Okay? That's not even, we're not even close to finding n of t yet. That is simply t prime of t, okay? Now we've got to find the magnitude of t prime of t. Now this is why I encourage you to use your calculators on this kind of stuff. Okay? So, alright, so look, now that we have t prime of t, let's find t prime of 1 and t prime of 0. Let's find the magnitude of t prime of 1 and the those are not necessarily equal. After we do that, we'll find the magnitude of t prime of 1 and the magnitude of t prime of 0, and we'll have our principal unit normal vectors, okay? All right, so t prime of 1. Okay, so we did some work. We popped in 1 for our t. We got these kind of nasty irrational fractions, and now we're just going to kind of estimate that as a decimal because we just want to show you what the heck we're doing. Josh, what did you get for the first term? That's fine. Comma.
And then,
comma.
0.179.
Okay. And I think that the square root of this squared plus this squared better be 1, right? Because this is supposed to be a unit vector. So that's going to get us, I believe that. That's pretty close. Okay? So now, let me go back to my last t prime of 1 is negative 0.35 comma positive 0.17. That's half of that.
Negative 0.3 squared is 0.09, and then 0.1 squared is not.
Okay, so we've kind of estimated our t prime of 1. We have to put this over the magnitude of t prime of 1, okay, so that we get the principal unit normal vector. And so we're just going to take this vector and put both things over about 0.4. Ted, is that what you got? Okay. And now you'll get, this is a unit vector. And now I can kind of graph it. So if I go back to this, we're going to go left twice as far as we're going to go up. Well, good. That kind of makes sense. Remember this? Remember how here I said I went up twice as fast as I'm going to go left? Well, good. Now I'm going to go left twice as far as I go up. And what do you notice about those two unit vectors? They are orthogonal. Okay, so this is the principal, let me change it to pink. This pink vector is the principal unit tangent, sorry, the principal unit normal vector. And it will always open up to the side of concavity, okay? And we're going to use it for some things, but I'll get into that later. But that is what we just found. The blue vector is your unit tangent vector, okay? So, look, this will be a fun little experiment. We should then, at t equals 0, get the vector 0, 1. So let's go back to here now, scroll down. And if you pop in a 0 for this, you're going to get a 0, right? So T prime of 0 over the magnitude of T prime of 0 is going to be 0, comma. All right. Here, you get a 0 plus 2 over radical 1. So you get 0, comma 2, and you start to get nervous because that's not what we wanted. But then you got to remember that we got to divide it by the magnitude, which is 2, right? Radical 4. Well, good. That's what we got. So we actually did something right in class for once. Okay. Thank you. Thank you. So, right now, here's what you have a decent understanding of. You know how to find the unit tangent vector. It's not that bad. You know what the unit tangent vector is telling you. It's not that cool. Okay? You know how to find the principal unit normal vector. It's the worst. And you don't really know what the principal unit normal vector is telling you, which is true. We do know that it's going to open up towards concavity, and then it's going to be orthogonal to the unit normal vector. So really, if you find your unit normal vector at a time, it might be easiest just to use the geometric aspect of this to find the other vector, if you're confident that you did it right. You understand what I mean by that? Rather than going through the calculus, you know that they're perpendicular to each other. All right. All right, so the best thing I could kind of do to explain to you what you're finding here is just give you a hypothetical position function with this orientation. So you got this R of t, okay? Now let's say that at this point you do some calculus to find the acceleration at that point. So how are we going to do that? We're going to find the second derivative of RT. We're going to pop in that t, and it's going to give us a vector. Okay? We're not talking anything new right now, just purely what we learned last week. Well, let's say that the acceleration was negative at that point. Okay? All right, well, if you could imagine the unit tangent vector looks like it would be going right about there, which means the principal unit normal vector, okay, so this right here would be n of t, and this would be t of t. Well, what we're going to do is take the dot product of a and t with the normal. Totally, yeah. Sorry, this should be my tangent, and this should be my normal. Thank you, Ted. Okay? So, what's happening at this point is that obviously our acceleration is going against our path. I just made that up, okay? So we use calculus to find that. So our object is going to be slowing down. So the magnitude of the velocity function is going to be, well, decreasing. Not necessarily negative, but going to be decreasing, okay? So what this means, another part of it, though, is this curve is, this object is about ready to turn sharply to the right. So what that means is we've got two different aspects of acceleration. You've got some of the acceleration, we would dot it with this, and you would get something that probably ended up like that. Okay? And then you've got other parts of the acceleration you would dot with this, and, well, it's just not orthogonal, or if it was orthogonal, you'd get 0. So you might get just a little bit going in that direction. Okay? And so that is how we are going to break up our entire pink acceleration vector, we're going to break it up into a normal acceleration component, okay, and a tangential acceleration component. So let's say that later on the graph, at a different point in time, our acceleration is more positive. Okay. Well, at that point, we're still going to have some is going to be tangential, and some of it will also be normal. And maybe you can imagine that there will be this much normal acceleration, and then about that much tangential acceleration. And if you can imagine this green rectangle, A of t is going, the acceleration vector is going to be A of t plus A sub n. I totally made up the pink vector at that point, just to illustrate to you what would happen if, let's see, what happens when, in this one, A acceleration dot t is positive, okay, and in this one, A dot t is negative, because those are going to be the two circumstances. All right, now it's also important to remember that if A dot t equals 0, what's happening? So what kind of shape is this thing traveling in? You got two options. It's either traveling in a straight line, and there is no acceleration. What's the other option? It's traveling in a circle. A circle over a parabola text, if it's traveling in a circle, it could have a speed that is not changing, but its velocity vector would be constantly changing, which means there is all of the acceleration is orthogonal to the motion, meaning it's pointed towards the center, and that's centripetal acceleration. Okay? So that's about the best I can do. Now, this is the only thing you really need to listen to. In a different textbook, so like in this How to Ace the Rest of Calculus book, they don't even really mention any of these things until they start to talk about this thing that's pretty important, which is called curvature. What I want you to think about curvature is that a really small circle and a circle whose radius is the Earth's, those two circles are similar, but they have far different curvature. Does that make sense? So curvature is going to be defined as how much a unit tangent vector changes over the distance of a curve. And so we're going to use T of t and N of t to find curvature. That's coming up next. Right now, you just got to kind of practice this and get through this crappy notation. Can I get a boom?